Good evening from Maine, or afternoon rather, sorry. It's actually 1:11 in the afternoon, Saturday, August 10th. Um, I finished off the last lecture, part two, with this slide here. Actually, it was this slide here, but this one here is a culmination of events of essentially 1.5 billion years of Archean time. And essentially what happened in the Archean is that we got the nucleus of the continent of North America, which we refer to as Laurentia, and then through the Proterozoic period, we acquire essentially, not the Proterozoic, yes, the Proterozoic, we acquire a lot of this terrain right here. So really Archean terrain here and then Proterozoic terrain right down here. Essentially these gray pieces were the first nucleides to form the core of Laurentia. You have the Ray, the Slave, you got the Wyoming, and then the Superior province here. And real estate started adding very early in the Archean right here through the Wapme, Orogeny, and what have you, through a series of island arcs. And then these three pieces came together right here, and thus formed this core in the Archean time of the Laurentian continent, which we now refer to as North America. And then in the Proterozoic, we have 1, 2, 3, 4 mountain building episodes. 3 is really not a mountain building episode. It was a rifting event that didn't quite follow through. But this whole area here was added from roughly Paleoproterozoic time to Mesoproterozoic into Neoproterozoic time. So this really here is from 2.5 to about, we'll say 900 million years ago. So another gigantic time period right here. Archean ended. When did the Archean end? Archean ended at 4.0 to 2.5. So this is 2.5 billion to about 900 million years right here, that we acquired this area right here. Most of these are late Paleoproterozoic and Mesoproterozoic into very late Neoproterozoic times. But this area here is real estate that was added onto the core, the craton right here, in the Proterozoic time. And the Grenville orogeny, which is this last one here in red, is about 1250 to about 9, was partially responsible for some of the source rocks of the Marginal Way. At least partially. When I say partially, it means that it helped create a mountain range that provided sediments that flowed, at least in this particular orientation, southeast, east, southeast. Marginal Way location is right here. So again, we don't even really have the land here yet that this is going to be where the Marginal Way actually resides. In the Phanerozoic time, about 500 million years on to about 300 million years, the Appalachians are created. And the Appalachians are created from sediments from this source and sediments from a source of island arcs and microcontinents that are out of picture right now, but they are somewhere over in here, and they will eventually make their way and suture onto this area where that's white right here of the eastern coast of the United States. And when this happens, this last mountain building episode right here, the Grenville orogeny in red, this one right here is a representation of the supercontinent of Rodinia. And Rodinia came together about, we'll just say between 12 and 900 million years ago. I'm sorry, 12 and 9, yeah, 12 and 9, 1200 and 900 million years ago. And this formation right here, this mountain range, the Grenville orogeny, is caused by Amazonia, which is now part of South America, coming together and colliding with the east coast of North America, and it creates another supercontinent called Rodinia. And Rodinia preceded Pangaea. Pangaea shows up in around 300 million years ago. Throughout time, we have periods where the continents have a tendency to come together, and the one that's before Pangaea is called Rodinia, and that is, this mountain range is a result of that. And when Amazonia decided to bail and take off and rift, you can see the rifting episodes kind of right in here. It left behind a piece of the Amazonia continent, and it's this chunk right here. So this chunk right here of rock was left behind by Amazonia as it departed, and we know that because these rocks have they're not similar to anything on this side. They're very similar to rocks of Amazonia, so we know that it's a piece of Amazonia. In any case, this lecture does have a lot to do with the coming together of Rodinia, the supercontinent prior to Pangaea. So I'm going to explain supercontinents. And supercontinents through time are very fascinating. The one that really I find most fascinating is Rodinia, because we've really learned a lot about Pangaea. We're 100% certain that this actually occurred. We are close to 100, if not 100%, that this actually occurred. Rodinia. Now, when we go further back, we start to lose our confidence, because the rocks have either been destroyed, the mountain ranges are hard to find, and there just wasn't as much mass as there is now today. So supercontinents through time, we have a group of supercratons right here. You can see pieces, superiors right here, Sclavia. I'm not really sure what that one is. It's hard for me. Valhara. These are just basically cratons that have decided to slam into each other and form the early nucleuses of the of the continents. We fast forward to 1.5, and there's actually something in between here. You have bits and pieces of things that come together. Nuna, sometimes known as, I believe, Columbia. There's another name for it, but this one existed about 1.5 billion years ago. Then, of course, we have Rodinia. You have, and this is much more, you can see things a lot better here. We can identify more here. This is Laurentia, Amazonia, Baltica, which is Europe. That is Siberia, I believe. Yeah, that's Siberia. I don't know what, maybe this is probably Western Australia, India. I'm not sure if that's North Africa. Yeah, I'm not sure about that one. And I'm not 100% sure of the names of these right now. But anyways, this is Nuna that came together, and we do find evidence of mountain ranges associated with this. And then, of course, this particular chapter is going to deal with Rodinia, Siberia, Amazonia, Baltica, I forget the name of that. You have South Africa, North Africa up here, India, China right here. And then these pieces all come together during the Neoproterozoic, roughly 1200 to 900 million years ago. They have it listed here as 0.8, but by 0.8 it was in its final days, and shortly after it began to disrupt and turn inside out, and everything rifted off of Laurentia, which is of course now North America. This is a Rodinia configuration, roughly 900 million years ago. And again, some of the pieces are absolute, others are a little bit more suspect. But as you can see, I was talking about that red area right here. This is the Grenville orogeny. And you can see it right here. This Grenville orogeny goes all the way around the globe, and you can find it on almost every continent, which means that if you find a mountain building event of the same age on all different continents, and the rocks are very similar, well, that only tells you that at some point there was a uniform mountain building event occurring at a particular time. So therefore, we consider that evidence of a supercontinent coming together. In other words, the rocks over here match the rocks over here. The rocks in Australia are deformed similarly as these are here, then they're roughly at the same time period. You have rocks in here. We've identified rocks in here now that connect East Antarctica to Laurentia. And again, this fold goes up and around through here. So we know, if these connect all the way through, well, it's pretty hard. If they connect and they match, then they must be somewhat interconnected. And that's our evidence for the supercontinent of Rodinia coming together. And of course, we were smack dab right here. This is where Ogunquit is at this particular time. It's in the middle of a gigantic mountain range. And this little point right here is probably a piece of the Adirondacks. The Adirondacks are like right here. So they are a Grenville orogeny. They are non-Appalachian. Rodinia, about 750 pieces are starting to move around. Again, you have the Grenville orogeny right here. This is a better representation of the way that the supercontinent may have looked on Earth at the time. Sometimes they put Amazonia here, and then this is further east. It's really up to interpretation. I'm not a big fan of this particular configuration. I sort of put Baltica here, and then Amazonia and Rio Plateau over here. But again, these are all interpretations. And again, this is actually by this point things are starting to rift. All of these dots right here are dated rocks and from dated igneous rocks, which means they were either volcanic or plutonic, and they all have the similar ages. So this map is probably a little bit older. I'm not sure the exact date on it. I don't have my reference on here, which I should. But in any case, you can see that this kind of wraps up around through here, extends over here. But these are all similar age-dated rocks, and they are of the Grenville orogeny. It's a worldwide event. It's a continent-continent collision eventually, and it actually follows very similar to the Phanerozoic, the Paleozoic building of the Appalachians. The more I look at the Grenville orogeny, the more I notice that it follows a very similar timeline and almost a very similar series of events. Basically, island arcs slamming into the east coast, and then eventually a continent-continent collision, which is exactly how the Appalachians are built. And this seems to follow suit. So the cycle is repeated, the Wilson cycle, and that's why I said that we would go through 2 Wilson cycles on this lecture. And this is the first. Once this comes together, we are going to start our process to build the rocks and the mountains that make up the marginal wave. But we need this to come together first, and now it has. And again, here we are, right smack in the dab of the middle. And this, make no mistake, this mountain range was the biggest at this particular time. May have even rivaled the Appalachians. We know it's at least as big as the Himalayas. This is more widespread. Mountains in this orogeny were probably in the order of 20 to 25,000 feet with ease. So a very significant event in Earth's history. This is a tectonic map. I'm not going to go into huge detail, but when scientists really start getting an idea and then it starts making sense, the work really starts to come together. And what I really kind of wish I could blow this up a little bit, but here's Ogunquit right here in the marginal wave. But these rocks right here, in other words, you can tell these came together because this layer of rocks here is exactly the same as this layer of rocks here. So, in other words, as these came together or rifted apart, you have basically matching rocks. So you have a layer of green here, a layer of green here, a lighter green here, and a layer. So that if you piece these together, you're going to see basically light green on the outsides, and then dark greens in the center. And that's basically saying that, this is saying you have oceanic arc sediments here, you have continental arc collisions here. And what's that showing us is that as this began to build, you had a series of events, and it literally shows you, if you have, basically if I was to do a line right through the middle of this, you would have the same series of rocks on each side. So in other words, you have continental continental and subduction rocks over here. In other words, you had something like the Andes over here and the over here, and then in the center you actually have the island arcs that slammed into it. So as the ocean began to close between these two, first it started to subduct under the continent and build and do a continental arc mountain building event, and then as the arcs offshore got closer and closer, they basically welded in. As the continent slammed, they pinched any island arcs that are in between them, and those occupy the dead center, which is the ocean-related rocks right here. These are island arc like Japan or the Aleutians or Indonesia. And when the Pacific closes, those arcs are going to get slammed in the middle, and they will occupy the center. Because once the Pacific closes, there's going to be a bunch of island arcs that are going to form as it begins to close. So if we were to bring Western North America to, say, Japan, the Philippines, the Japanese island arc, Taiwan, all that stuff is going to get sandwiched, and it will make an area like this, a series of island arcs. Meanwhile, on the actual continental side of Asia, you'll get a subduction underneath the edge of the craton, and that will produce a continental arc. And you have both of these. And of course, if there was subduction on both sides of Asia and North America would also have its counterpart over here. So it's kind of a lot to think about, but at the same time, it does make a lot of sense, and that's how we know that there is a suture zone there. This is Rodinia. I have no idea what this is. It's obviously it's just I don't know what this is. Anyway, this is Rodinia, about 950 million years. And again, I'm doing this because there's a lot of different interpretations of what we were actually looking at. So if I was going to, this is Ogunquit again right here in the center, I would say that this is probably Amazonia right here, adhering to really, now we kind of think it's over here, and this would be rotated a little bit more this way. But this is basically the supercontinent of Rodinia, which what it may have looked like, and it may not have been, like you think of all land. It might have been a series of areas where continental crust is sticking above the water, and meanwhile there's interior seaways that are occupying the center parts of the continent, kind of like during the Cretaceous when there was a seaway between the Appalachians and the Rockies, or right now there's an Empiric Sea in the North Sea of Europe between England and, say, Norway, Germany. The North Sea is an Empiric Sea, kind of like this. It's anywhere we have continental crust that's being flooded. They generally are shallow. I'm trying to think of where there's another one. Yeah, you could say that the Chinese Sea, or the Sea of China, I forget what it's called, but that would be an Empiric Sea because it's actually on continental crust that's flooded and not actually over deep oceanic crust. Maybe if you were to use your imagination, this is kind of what Rodinia may have looked like at its time. Lots of volcanic activity along the margins. I'm assuming that these are stromatolites. The atmosphere is a little bit different due to the high amount of CO2 still in the air. Oxygen is definitely making its way. The stromatolites have been producing for a while, but we do have a lot of soot and ash in the air from a lot of volcanic. When a supercontinent comes together, there's a lot of subduction. There's a lot of volcanic activity, and there's a lot of ash in the air, which would make sense that it may actually it would alter the color. We've seen wildfires produce vibrant orange and pink sunsets, so it makes absolutely perfect sense that this may do the same. Okay, so this is where it gets kind of complicated, but this is the stuff I really enjoy. In order for the Appalachians and the sediments to make coastal Maine, or really New England in general, we needed a source. And that source came from the Grenville orogeny. Here it is in detail. We infer that it probably went out this far. So in other words, the area that Maine and New England occupy in the East Coast was definitely a gigantic mountain range when the continents came together, and it would have cut, this whole area would have been, one big giant mountain range. Um, so this is referred to as the Grenville orogeny. It is the building of Rodinia, the supercontinent, and we have a Himalayan-sized mountain range that is right here. It deformed into the actual cratonic nucleus of Laurentia. It caused all sorts of deformation through here. There's rifts, there's faults from this. This was a massive, massive continent-continent collision. But like all supercontinents, its time was limited. And as this began to melt down, as it began to erode, it began to spread rock this way and rock this way. We have rocks from North America found on the western side of Amazonia, and likewise we have rocks over here that are from Amazonia on Laurentia. So we know that they were connected. It's kind of how it's like, imagine rivers flowing out to the lowlands. You would carry sediments from these mountains just like rivers do today. Well, you also had a landmass over here that would be dumping the same sediments this way. So when you go to a beach and you pick up a handful of sand, well, let's just say that we're at Ogunquit Beach. I'm going to look at that sand and I'm going to say, okay, where did this sand come from? And I can trace it right back to the Mount Egamenicus Pluton, because the Josias River, the Ogunquit River, all have been eroding this Pluton. But it's not just that. There's the Webb Hanna Pluton. There is the Alfred Pluton. There's a whole bunch of igneous rocks that are upstream of Ogunquit Beach. But more than that, Ogunquit also has a massive amount of glacial sands that have been deposited, that have been grinded from this area up in here. So not only do we have plutonic rocks, sands derived locally, but we have sands that have been brought down by glaciers from, God only knows how far back. So when we look at the sand grades and we analyze the signatures of them, meaning the zircons and what mountains they form from, we find that there's a whole range of them up in here. But we do know that they come from partially, the majority of them right now come from North America. Or if they don't, they were residuals that were left over from rocks that were formed during the Grenville orogeny. But the point is, when you go to a beach and you pick up that sand, all you got to do is find the nearest river, and that's where the source is coming from. And that's kind of how we figure out, where these rocks, where these rocks were formed, and what procedures and what interactions with other continents have to do with them. So anyways, like every good supercontinent, its time is limited, and eventually these wear down, and the amount of weight that this mountain range put onto the crust was, you just can't even imagine. In any case, it bends the crust down, the crust gets very thick, it goes down into a hotter region into the mantle, and due to the pressure, it stays relatively stable. Well, once you start to remove all this weight and spread it out on the sides, you are going to find that all that heat that was generated down in the cores or the roots of these mountain range are going to start to melt. And it's called decompressional melting. And once they start to melt, it's going to start basically becoming more buoyant, and it's going to start injecting plutons into these mountain ranges as they erode. I might even add that a lot of the west coast, like the deserts and the sandstones, are derived from Grenvillian rocks. So in other words, this mountain range just deposited stuff all the way back. I mean, into the Arizona, Colorado, New Mexico. It is just a massive amount of sediment that was produced from this. So again, as the mountain range wanes, as it erodes, it begins to lift. Melting begins to occur, and guess what? As the pressure becomes less and less, the melting begins to increase. It begins to produce more volumes, and if you get enough of it, and there's enough upwelling underneath this suture, you are going to split it. And over here, is the Iapetus Ocean opening. And the Iapetus Ocean is the ocean before the Atlantic. And these green lines right here represent the area that the Iapetus Ocean opened up in. In other words, when Amazonia left the east coast of North America, it fractured right along these these lines right here. So in other words, when it left, we had a huge embayment right here. In other words, there was a gigantic, sort of bay, and a big chunk of North America took off. Then you have so there's always bays and promontories. So here's the St. Lawrence promontory. Here's the bay. You've got the New York promontory, which is now, we think, it's pretty much the Adirondacks. And then you come down here. There's a few more embayments, and they're much smaller. And then you have a huge one right here, because this chunk of Laurentia took off. It broke off and went with South America. So you have all sorts of things, but in any case, it kind of is similar. It follows kind of the same pattern of the United States today. However, it's one episode before, it's one cycle before, so it split much further back. Today, if you go down here, you can see that it's split much further out, and this is the opening of the Atlantic. So this is the opening of the Iapetus. This is the opening of the Atlantic. So this is 800 to 650 million years. This is the opening of the Iapetus Ocean. This is the ocean that a lot of the sediments got dumped in from the Grenville orogeny, and it's these sediments that got crunched and metamorphosed and uplifted that make the Appalachian Mountains. And without this, you would not have the materials to produce the Appalachian Mountains. And that's why this talk needs to go back for at least 2 cycles, because in order to build something, you need materials. And this is where a lot of our materials come from. Not all of them. And I'm going to get to that in a little bit. So fast forward another 200 million years, and the Iapetus Ocean has lived its cycle, and it is now closing. And this line right here represents the Iapetus suture zone. And what happens is over the course of from 480 to about 270 million years, a series of island arcs come. As the Iapetus Ocean closes, island arcs start slamming into the side of North America, and then a couple of microcontinents, Avalonia, Magma, and Gandaria. Gandaria is sort of a mismatch of arcs and oceanic crust. Slam in and build these Appalachian Mountains. The old sutures way back here, and even today, you can find this line. I believe it's called Cameron's Line in Connecticut. But that is the suture of the Appalachian Mountains to the Grenville terrains. And as this happens, we're going to go through this in fairly great detail, but this is the Appalachian Range right here. And obviously it goes much further out. Africa would be right here when it's all said and done. South America is up down here. But yeah, these are the Appalachian Mountains. And then, again, this is the formation of Pangaea when this comes together. And like every great supercontinent, it has its time in its time in the sun, and then it decides that after the Appalachians, which are also a Himalayan-sized mountain range, begin to erode, and again, the crust, the core, of the roots of the Appalachian get pushed very deep into the mantle, because when continents come together, they stack, the crust gets unusually thick. Like in the Himalayas, I think it's like 60 kilometers right now, and usually the crust is about 35. But that deep area of crust is underneath, and it is into a much hotter area of the mantle. And the only reason it's not melting is because it's kept under pressure. But once you take the weight and these mountains erode, that pressure gets, the area gets lighter, things begin to lift, and you have what we call, as I said earlier, decompressional melting. And the melting begins to melt the roots of these mountains, and you have upwellings. And if it gets, if the machine gets going hardcore enough, it's going to split the continents in two. And lo and behold, just like the Iapetus Ocean suture, just like the Iapetus Ocean rift zone, the Appalachians also have a rift zone similar to that. And it almost follows, sort of similarly, the outline of the old Iapetus suture before it. This right here is where the continent of Africa decided to rift and separate and then leave and go east to its present position today. And if you've noticed, it has a very similar track to the original Iapetus Ocean rift. There's a couple of differences to it, but for the most part, you can kind of say that it follows it. So Grenville Mountains, Appalachian Mountains, Iapetus Ocean Suture, Atlantic Ocean Suture. And, you know, there's lines in here that are very difficult to see. The green are Iapetus sutures, which again, these orange ones in here these ones in here are areas where the Atlantic Ocean Africa tried to rift, but it didn't quite make it. It ended up moving further east. There's a couple right down in here that are associated with rifting of the Atlantic Ocean. The Newark rift zone down here in New Jersey, New York. You have one up in Quebec. You have the Connecticut. You have the Connecticut Rift Valley. That is an area where the continents tried to separate and actually flooded with basalt. But for one reason or another, it didn't quite make it, and it ended up moving east. And a couple hundred miles east is where the actual rift occurred, and then Africa departed. So a lot of information here, but it really explains how the oceans are kind of related, and how when continental cycles come together and break up, they may actually follow preceding sutures and rift zones. This is the Atlantic Ocean today as we see it. You have if you notice this pattern right here, sort of mimics exactly what this is and what this is. Take a good look. You see these transform faults, and then you have the main ridge right here, and you have transform faults, and you have the main ridge. Transform faults right here, and then main ridge. And is exactly, both of those are very similar to what you see today. And once the ocean gets to its, widens, you'll have these faults, because there's no way that this piece of this spreading center is going to spread uniformly. So you always get perpendicular faults to it. And we think it's these perpendicular faults that actually initiate subduction in the far areas, in the older areas of crust. We're not 100% sure, but it seems likely. But this is the Atlantic Rift Zone, and again, compare it to what you see here. This is how it started. This is how it ends. All right, 1.0 billion years of east coast of North America Laurentian tectonic history. So I'm going to use this diagram here for a few times, and this kind of lays it all down for us. We start down here at around 1 billion, and this is the Grenvillian orogeny, and this is basically prior to 1 billion, Rodinia comes together, and you have the Grenville orogeny, and then you have Rodinia. That's 1, Rodinia 2, and then around 800 to 700 million years ago, you end up getting plutonic activity in the southern area, which means that the mountain range has now eroded and rifting is now starting to take over, and that's represented by this. These two arrows going in opposite directions. Opposite directions means spreading centers. And this is the Iapetus Ocean from basically 700 million to about 540 million years. The Iapetus Ocean is opening. I'm not sure when it reaches its peak, but it's sometime around here, because it is in this period of time here that the Iapetus Ocean starts to close. So Iapetus Ocean, for at least 200 or 300 million years, opens up, and then it begins to close. This is the end of the Proterozoic period at 542, and this is where we launch into the Paleozoic period, and this is when life really explodes right here, and we know much more about these time periods than we do down here, but we are starting to fill in the gaps, and this is for the upcoming lectures a little bit later. So we're going to concentrate right in here. This is basically showing us that we have a ton of plutonic activity, probably beginning to relate somewhat. I'm not 100% if this would still be rifting and spreading. So you got the Iapetus Ocean, you've got the Taconic Seaway. The Taconic Seaway was formed when an island arc comes together. I'm sorry, the Taconic Seaway is a seaway that forms off the east coast of North America, as an island arc forms way off in the distance in the Iapetus Ocean, and slowly makes its way towards North America, or Laurentia, and that is represented by this. So the Taconic Seaway is very far away. It's wide open at this point, but around 480 million years, or around 500 million years rather, the tectonic seaway begins to close because the island arc that was previously offshore is now beginning to make its way towards North America, and it's going to actually collide at about 480 million years ago, and that is known as the tectonic orogeny, and this is the accretion of the island arc. A short time later, we end up having the closing of the Iapetus Ocean as subduction continues. Originally, subduction was east-facing, going underneath the island arc as it was approaching, but then you have a polarity reversal right here, and the subduction now goes under North America or Laurentia, and you have behind it a chunk of what we think is Amazonia. A chunk of that continent broke off, and we call it a microcontinent, and that microcontinent is called Avalonia. And as Avalonia begins to collide, make its way towards North America, right around in here it collides, and this basically creates most of the real estate of New England. And this represents the closing of the Iapetus Ocean. You have numerous subduction zones. Once the Iapetus Ocean crust subducts under North America, Avalonia accretes to North America, and then there's an ocean behind that called the Ray Ocean. And as time goes on, various terrains behind Avalonia make their way over and slam and accrete onto the east coast of North America, and thus close the Rheic Ocean. And then finally Africa shows up, and we have a huge mountain building event here. Not much in the northern Appalachians, but huge down in the southern Appalachians. And then Pangea comes together, and Pangea is in its heyday. And then about 200 million years ago, the rifting begins, and the Atlantic Ocean begins to separate. So two cycles right here. You have the coming together of the Grenville, the opening of the Iapetus, the coming together of Pangea, and then the opening of the Atlantic. Okay, so Grenville orogeny, 1250 to 900 million years ago, Amazonia, the western Argentina, South America collides with North America. As I just went over that, this is a chunk that was left behind. This is the mountain range. This is created by Amazonia slamming into Laurentia. Back around 1200, well, we'll say about 1 billion years ago. And it created, again, a Himalayan-sized mountain range. When this occurred, the deformation went back into this area here. We call that the foreland. It's, again, one of those things, how did this get deformed? Well, we know that because it took a mountain range to do it. So, this is a mid-continental rift that tried to open up right around the time that this was starting to occur. It was almost as if, like right here, this is where the superior craton broke apart. Again, this was trying to occur too. We don't know if it was related to the Grenville orogeny or not. It could be a back arc spreading area. We're not 100% sure about that, but we do know that there's an area here that tried to actually erupt and split. It just never occurred. So in other words, North America could have been broken right in two. It just never happened. All right, so Paleoproterozoic. This is 1.65 billion years ago. What we're looking at here is what the artist rendition. This is Blakey. He's famous for making these maps. And we're kind of looking at what North America may have looked like at that time. You can see the Canadian provinces here. You can see that probably Hudson Bay would have been somewhere in here. This is an eastern rift zone off of this. This is the superior craton right here. The Wyoming's down here. And these are island arcs that are going to end up getting slammed into North America. There's subduction going along the coast right here. What would I say? So this is Colorado, this is New Mexico, Texas would be right here. So the majority of the East Coast isn't even here. We're somewhere back in there, Michigan, Indiana, Illinois. Anything down past, say, Missouri's not, it doesn't exist. And this is probably how it looked. You had a passive margin off to the west, and you had a very active margin right here. And these are island arcs associated with that. And these mountain ranges, this is the Yavapai, and this is the Mazatl. And both of these occurred in the Paleoproterozoic. And they resulted from island arcs that were on their way over to, they were basically, as subduction was happening underneath Laurentia here, it pulled the crust over, and as it did, various island arcs formed offshore and ended up being dragged and slammed onto this, making all sorts of new real estate. The first episode is shown here in green, the Yavapai, and then the Mazatl was shortly after that. So in other words, this mountain range occurred as an island arc accreted, and then behind it another one occurred. And you can see that this is a thrust fault. So in other words, the land as it hit, as the island arc came in and went up, it subducted, the crust before it was subducting under, but then once the arc hit, it ended up being pushed up onto the crust. And it's the same thing with this. The ticks are always on the upper side, so this one hit, it got thrust up on this piece of crust here. Then we have at 1.45 billion years ago, this is now, we've adhered the Yavapai and then the Mazatl right here, so we've added more crust right here. I don't know what this is right here. This could be Antarctica over here. I'm assuming it probably is because it was definitely on its way over at some point. We have another series of arcs right here that have been adhered onto this. Now, what happens here is very strange. We have what seems to appear in this crust right here. It's as if when this mountain range began to, or these arcs, these mountain ranges created by these arcs began to erode and display, and end up getting lighter, because again, these arcs are going to push, they're going to create a mountain range that thickens the crust and pushes it down in. And like the continent, but to a lesser extent, the roots of these mountain ranges are going to be pushed way down. But as they erode, they're going to get lighter and try to come back up. And what happened was this area right here, which is represented by this green right here, began to lighten because the mountain ranges are right along the edge. And we ended up getting decompressional melting again. As the crust got lighter, things began to melt at the base, and when things melt, they become buoyant, they try to go up. And it ended up trying to punch through, or at least to some extent, this crust began to thin and spread each way. I don't know, I'm not sure it spread, but it definitely thinned out, so it must have spread somewhat. And it produced a ton of felsic rock material that created a very large portion of the southeastern United States, and part of the Texas, the Mississippi embayment, and the western part of southern Appalachians. Now, what's interesting about this is that the rocks produced of this were mostly felsic, meaning they're granites and rhyolites. Now that makes perfect sense, because when you have a massive amount of decompression melting from arcs, you are going to produce a lot of lava and magma beneath it. However, the initial series of it, the initial start of rifting is going to push magma up through the crust. Well, the crust is being more felsic. So in other words, before it starts making oceanic crust, or the actual plates split apart, you've got to melt a ton of continental crust. And continental crust has a tendency to be it's lighter, it's more buoyant, it's felsic. So what we think happened is a new rift zone began to attempt to form here. It just never made it. And so what happened is you had the initial melting and decompressional melting of the lower basement of the crust, and it got injected into the upper levels of the crust and produced a massive amount of felsic rock, meaning granites. And when they did erupt, they produced rhyolitic lavas, which are very felsic and explosive. So this is essentially what we call possibly a failed rift system. In other words, a continent tried to break apart in here somewhere. It just never happened. And so that's why the Granite-Ryolite province is a very strange episode along the southeastern margin of the United States that really still kind of baffles scientists. What really happened there? Why didn't it continue? Why didn't it? And it went through the cycle of thinning. It went through the cycle of producing melts. It did the cycle of producing plutons and intrusions and volcanic activity, but for one reason or another, the crust just never thinned enough to actually rift and split, and then create a new island arc and a new mountain range. Now we get to the Mesoproterozoic, the Grenville orogeny. So this is the one we were just talking about. This is the way it kind of looked. You now have Amazonia right here, probably Baltica here. And you have a series of island arcs. This would be sort of, let's see, yeah. So this would be New York right here. New England would be up in here somewhere. You have basically this is the southern Appalachians, or not the southern, this is the southern Grenvillian Mountains. And they kind of, the East Coast kind of has a bulge that comes out, sort of near the Carolinas. And this may have been produced, or at least originally had, when the Appalachians sutured on, maybe this was, caused by this actual prominence right here. In any case, Amazonia slams in, the island, the trenches right here get subducted. They subduct this ocean that is here, which to the best of my knowledge, I do not know the name of it. And you produce a massive mountain range right in here. And that is represented by this red right here. This is the area that tried to rift off but never made it. And then this is going to come in and create this right here. And there'll be another piece down here that creates this area right here. But as you can see, this Granite-Ryolite area remains relatively stable, does not rift, and then gets deformed as this pushes into it. So that's the time chart for that is the Grenville orogeny in a nutshell. And now we are at we're at the Rodinia supercontinent formation, which is right here. We brought together the Grenvillian rocks, we closed the ocean between, and now we have the supercontinent of Rodinia, and now we're going to start breaking that up. So, the Grenville orogeny. You start here, you have Amazonia, you have North America, they have, this represents where we are, and this is sort of represented by this right here. So you have the Grenville orogeny. Eventually, the Grenville orogeny is going to erode. As it erodes, the mountains become lighter. This area ends up becoming more buoyant, which is represented here, and then you end up getting continental crust, instead of coming together, begins to start moving away. This is the Grenville orogeny here. This is the deformation of the Grenville orogeny over time when the continents finally do collide. And then eventually, this is the rift zone that after the Grenville orogeny, and this, which is represented by this piece right here, is represented right here. And of course, you have Antarctica and Australia over here, and then there's a bunch of tectonics going on over here. And you can see Australia and Antarctica represented here. So there was action going on the west coast, which I'm not going to get hugely into, but we do know that pieces of Antarctica and Australia match Grenville rocks that are over here. And you can see that this is the mountain range, and it just continues, right along the east coast, right up into Europe, or what is now Europe, goes right down through here, and then right up through here, and southern Australia has pieces of that. I believe that's southern Australia, yeah. And of course, Antarctica has, there's a piece of that extends onto Antarctica, and then when the mountains begin to rift, you actually get decompressional melting rift magmas, and you find those also on the side, and you can see them here, and these rocks match on Antarctica, Australia, as well as the west coast of Laurentia. So this right here is represented by this, and then this right here is represented between here and here. So you have the rocks begin to erode, they begin to thin, and then you have separation right here between 900 and 600 million years ago, when the actual Iapetus ocean formed. So the coming together, the subduction here, the actual mountain building episode, the supercontinent here, and then you have the rifting event here. And the rifting event is basically represented right here. And then eventually this becomes a passive margin. It looks like this. And just to give you a prelude to what's coming, this passive margin will begin to close. because we'll get an island arc offshore somewhere in the Iapetus Ocean that will start coming towards the west. This is the passive zone of the east coast of the United States. Roughly about 700 million years ago. Has lots of sediments, has lots of reef deposits. Actually, probably is a good reason why life got its chance. You had some amazingly clear water over in this area on the east coast of the United States. Had just beautiful water, looked a lot like the Bahamas. It was in the tropical area, and life just loves things like that. And it really wasn't until this time that we got a really good passive margin to do this. So this is the representation of the tectonic mountains. This is what is going to become the main mountain spine of Vermont. This eventually gets dragged over and slammed into it, so it's right here. We have a piece of Amazonia that is rifted off. This is eventually going to get dragged over here, and it does. This gets slammed over here. You have a rift zone underneath it and one underneath North America now. And then this is Africa here. So this ends up getting welded on during the Acadian orogeny. So you've got the Taconic Mountains, you've got the Acadian Mountains, these are Maine and New Hampshire, and then you have the subduction going underneath Africa, and then Africa eventually welds on during the Alleghenian orogeny and creates, the full extent of the Appalachian Mountains. And then once this has come to climax, you'll begin to rift this, and it will begin to erode, and you'll have the cycle repeat right here. And then these two things will begin to, Africa will go her way, North America will go her way, and this happens right at the beginning of the Mesozoic period, which is the dinosaur period, about 170 million years ago. And then present day, Africa is now gone, pieces of it are left, pieces of Avalonia are left, pieces of the island arc are left in Vermont. You have a valley and ridge province in back of that, so this is more southern Appalachians, and then we have a nice passive margin again. So, the Grenville orogeny representation on the Wilson cycle. So, we put it as here. The Grenville orogeny is a continent-continent collision, and in its heyday, it was as big as the Appalachians. So, right now we're here. This is the Atlantic Ocean spreading. Eventually, we will end up having a subduction zone, and then the Atlantic Ocean will close, and then whatever continent. Probably Africa, or I would think it would be Africa, but either Africa or Europe are going to end up coming together and slamming in and making another Himalayan-sized orogeny on the east coast of the United States. And again, that will start to erode. It will start to get lighter. The roots will melt, and you'll start getting plutonic activity being pushed up. And then eventually it'll be eroded flat, and the continent will be nice and stable. And then eventually this area here will begin to start, this melting. This should be still melting. This will continue to thin, and once it reaches a certain point, it will begin to thin enough where more melting will occur, and it will start to separate the two pieces of land. Here is the Grenville orogeny in the affected terrain. This is sort of the process of it occurring. You have Laurentia here. You have Amazonia here. You have a subduction zone going underneath Laurentia. We know that because there's volcanics and plutonic activity, from New York up through Quebec, Montreal, all the way down through, Indiana, Missouri, Texas, and that's all associated with subduction of an ocean that was off the East Coast prior. To the Appalachians, and Amazonia made its way over. It ended up colliding with Laurentia and producing a massive mountain range. And you can see right here, the subduction is gone. The Amazonia has now collided with North America, producing all sorts of sediments. And then eventually, these two erode enough the mountain range, and you have they begin to separate, and you end up having crustal thinning in here somewhere. And then the Iapetus Ocean opens up right here, and you have subduction, of course, going off to the west, and then Laurentia basically has a nice passive margin for a good 100 million years or so, and this is really where we think life goes from simple-celled organisms to multi-cell organisms to things like that can produce things like shells and what have you and things like that. So this is really a big help as far as life's evolution. This is around 500, 600 million years ago. This is just an offshore island arc. It's not really, I don't know what this really, this is Amazonia. I don't know what collided on that. This is just an artist's interpretation of it. This is the affected area. So anything in this area is hugely deformed by the Grenville orogeny. These are deposits that are, came off of the Grenville Mountains as they eroded. These are pieces of the Mazatal orogeny, and then of course we have pieces up here. This is the Trans-Hudson orogeny right here. This is the Yavapai. This is the Mid-Continental Rift. We have the Granite-Ryolite area right here. So this is just giving you an idea of the amount of things that have happened in the last say 2 billion years or so. A little more of the Grenville orogeny. This is a deformation map. Essentially, this is the main area that it occurred. Everything out here with what we call this line right here basically represents how far back it really was deformed. This is sort of the front. There may have been some deformation here, but right in here is where it really the main mountain building episode occurred. Actually, it's kind of like right here. These are more Yavapai and Mazatal orogeny here. Right down here is a place called Mars Hill. It's an area where Grenville rocks actually pop up through the Appalachians. You can see some here in western Mass and Connecticut, some right here down in New Jersey, New York, and then down further in the Carolinas. And these are actually pieces of Grenville orogeny that pop up through. But yeah, this is essentially where you've got the majority of the Grenville orogeny happening. Extent of the Grenville Train along the northeast. So I put this here because this line right here is known, I believe, as Cameron's line, and you can actually find this if you know where to look. And what you have here is you have everything west of this line is essentially basement rocks are considered Grenvillian, which means they're about 1 billion years old. Everything east of that is considered Appalachian, which is generally less than, we'll say, 400 million years old. And this weird sort of yellowish mustard color is buried, and then the brown is where they actually stick out, and you can physically go and touch them. So these, Berkshires have some, the Green Mountains have some, the Adirondacks are all Grenville terrain, and that's why we say that the Adirondacks are not part of the Appalachian orogeny. They are twice as old, and the sediments are different. They are just different in every single form. So that is a misnomer that the Adirondacks are part of the Appalachians. This is sort of a complicated graph, and what this is really showing is you have the suture right here, and I believe that this is. Sometimes it takes me a minute to get a good look at this. I believe that this is an area of. Okay, so this is probably further up north, I think, and then this one down here is sort of Canada, yeah, Canadian. Okay, continent collision in the U.S. Okay, so this is United States right here. This is probably southern New England. That's what I'm guessing. So southern New England, I mean not southern New England, the southern Appalachians, you have the thrust of the Grenville Mountains going up and over the Moho. You have Gondwana. This is the Appalachian terrain. There's a sort of a fault right here, and this gets slammed into these are the Grenville Mountains. This is the Grenville basement. These are the Appalachians, and this is the suture. And these ride up over the Moho, and these sort of just welded onto the actual the Grenville. So Appalachians, Grenville. Down here you have a continent arc. This is probably Quebec area, or not Quebec, but Newfoundland. You have Avalonia, which is a part of. This is a part of Well, we think it's between, it's a piece of northern Amazonia, possibly part of Africa. Gander is a bunch of island arcs that are associated, that rifted off of probably, I think they may even be, this may be more African affinity. I don't know what this is, I think this is Taconic. But anyways, this is the Appalachians that have been sutured into this is the Grenville Mountains, this is the Appalachian Mountains, and again, you can see a thrust where they've been thrust up onto it. And then the Moho's back here, but this is basically the gigantic roots, and there's thrust faults right here of the Grenville orogeny. And then down here, this is sort of New England area, and we have a big part of New England is the Ganderia terrain. This is Gander, and this is the Taconic belt right here. This is Vermont. Yeah, this is Vermont. And you can see that as this collided, these got thrust up over, again, over the Grenville terrain, and you have a nice suture right through here. So the island arc of the Taconic belt got slammed and rode up over the Grenville rocks, and then Gander came in and slammed into the Taconic belt and pushed it even further up over. So this is sort of the Grenville orogeny in a nutshell. Southern Appalachians, very far north, probably Canadian, and then this is the New England Maritime. This is the New England and Maritime area. I'm not going to go into this. This is just way too complex, but this is really like everything you wanted to know about the Grenville, but we're going to bypass this because this is just too much and it's too small for me to really go into great detail. So, all right, so Rodinia comes together. Well, Rodinia must break up. And oftentimes we find that continents have a tendency to break up in triple junctures. So, in other words, it isn't just one straight line that splits these things. It has a tendency to split at 120-degree angles 3 ways. And this map is a good idea of really showing it. So down in here, we have a triple junction, and it's likely that this might have been the part where it begins to occur. And this was probably affected by the subduction zones that formed on one side. So in other words, as this is subducting here, it's pulling this way, and as this is subducting, as this is going underneath here, it's pulling this piece this way. So this is being split from here, and simultaneously this is being split from here. And then right in here, I'm not really sure what's happening, but actually this is rotating, so this is being split here, and then this is being split. And eventually, this is going to find its way and go up through here, and then split all of this off of here. And this will go this way, this will go this way, that will go that way, this will go this way, this will go this way, and then Laurentia is now left all alone. So now, as the erosion has begun to take away the mass of the mountain range, this is representing where we are in the Wilson cycle. This root has melted, it is starting to inject things, and we are migrating over to stable continent. And then once the stable continent becomes thin enough, and then melting continues, melting should be continuing here. You're going to go to here, and this is when the breakup of Rodinia happens, and this basically thins the crust and forces both pieces apart. And that is represented by this on this map right here. The Grenville Mountains have now eroded. These are becoming thin, the crust is thinning, and these are beginning to pull apart, and this is where we are in the Wilson cycle right here. And we are about to go into a passive margin, and this is the rifting of Rodinia. So around 700 million years ago, this might be what the east coast of Laurentia might have looked like, or the west coast, who knows. But in any case, you have a pretty much barren landscape. You've got a blue sky. You've got some water, it's the ocean here, but no life yet. These are not some life, but these are probably stromatolites if there is life. Life is still very simple at this point. The Iapetus ocean rifting event. So this is the breakup of Rodinia, and again, these are the rifts that formed on the eastern side of the continent as you see it today, and this is where Amazonia and North America began to split. This is the exact location where everything just pulled apart, and then an ocean filled in right here. And again, you have the St. Lawrence promontory, you have the embayment here, the Quebec, and when the Appalachians are formed, this whole area gets filmed during the Acadian orogeny and builds this huge chunk of New England right here. We also have a very large embayment down here, and this ends up getting a piece of this gets left behind when the Appalachians form. It fills this area right here, and it forms this area, fills this area here. And when the Appalachians split, a chunk of Africa stays here, and a chunk of it stays here, and we have these promontories right here. So now we are here in the cycle. The Iapetus Ocean is forming. This is 600 million years ago. That's represented by the splitting of the two continents, Amazonia and North America. We do have some plutonic activity. The crust is thinning, but we now are going into a passive margin right up through here. And this is where we are on this map right here. We are now into a period of quiet times as far as rifting goes. The Iapetus Ocean is now in full swing, and the west coast of North America has a nice, mellow, wide open. Looks very much like the Bahamas. Beautiful, crystal clean water. Life, it's calm. There's no volcanics going on. There's no earthquakes. It's just a nice area where life is going to get its chance to get its act together. So now we are in the late Precambrian, about 550 million years ago. Here is our location right here in Maine. We have Amazonia, which is going, South America, which is going this way. North America is going this way. And these are in relation to each other, by the way. And you have Baltica, Europe going this way. And as I said, there's a triple junction right here. And this is the Iapetus Ocean right here. This is now becoming wider. It's a nice big fat ocean. It's going to continue to enlarge, and life, it really gets its shot to get going right along here, because this area no longer has volcanics. There's no trench. There's no earthquakes. There's, this is a nice peaceful, the ocean isn't too big, so you're not getting gigantic wave action. You're getting a nice, and by the way, this is right near the equator, so this is real nice and warm, and the water is just perfect for life to get a chance at going. And about 560 million years ago, this is just a global view. Amazonia down south, the Iapetus Ocean right here. You are here. I always like that. Again, beautiful continental shelf, nice passive margin. In fact, nice passive margins everywhere right now for the most part. And this is, like I said, this is when life really gets its start. And on this chart, we are represented right here. So this is somewhere offshore. The Green Mountains are or what's going to make the Green Mountains is starting to form. Somewhere way out in the Iapetus, there's an island arc that decides to start forming. In other words, one piece of crust, oceanic crust, goes under another, and we have an island arc. And as time goes on, this is going to start pulling its way over to this passive margin and create the Green Mountains of Vermont. And we are right here on the cycle. And North American East Coast on the Wilson cycle at 550 million years ago. We have now rifted. The Iapetus Ocean is in full swing. We have a nice wide open ocean, and we are represented by this point right here. And we have nice passive margins, nice beautiful water. Life loves it, and the ancestors of us are really getting their act going. And we're going from not just single-celled to multi-celled organisms, but we are actually going to not just multi-layered organisms, but organisms that have specialized cells. And this is when life evolution really takes a huge jump of a leap of faith here. And then soon we're going to get an offshore island arc that starts heading its way as this ocean's going to start to close eventually, and that's represented here by subduction starting on this side. And I mean, that's not 100% accurate, but it gives you the idea that one side is going to start subducting, and it's going to start dragging the piece over, and it's going to collide with the east coast of North America and make the Green Mountains of Vermont. So we go from a passive margin to an active margin again. And if we were to look at get an idea of what the North American East Coast looked like, around 500 million years ago, 550 million years ago, you would have organisms here. This is not quite right because we do not have shelled organisms yet, but what we did have is a lot of carbonate carbonates coming down and being deposited into a beautiful area of nice, warm, shallow water that's very clear. You have the eroding sediments of the Grenville Mountains depositing all this carbonate into a nice, warm, shallow sea. We are not producing shells yet, but we are getting close. And this is what the east coast of North America looked like at about 550 million years ago. This is Earth about 600 million years ago. You got a nice, again, you've got some volcanoes maybe in the distance, or probably not. You know, there could be areas, but there are areas in the Earth, and the East Coast probably looked a lot like this. Very, very bluish water. You got stromatolites, very tropical, very warm. But as the tectonic mountains start to come, as the tectonic island arc starts to come our way, you would start to see something like this. But that won't be for another 120 million years. I wanted to come back to this. This was behind this actual figure. At 560, we didn't really have enough carbonate materials yet, or we didn't have the ability to produce skeletal reef deposits. However, as we get close to 540, 520, these do start to form. So it just took about 10 million years, and then once we do get carbonates forming, we have a huge reef deposit that forms off the east coast of the United States. And you can find it in New York and western Connecticut, Mass, and Vermont. And these reefs were compressed into making marbles. And you can find marbles all over the western perimeter of New England. And these marbles are what were once reef deposits on the passive margin of the East Coast. So I just wanted to point that out. Again, I just went over this. Tropical area, beautiful, and as the tectonic island arc starts approaching the east coast, you're going to start seeing volcanoes. But again, beautiful warm reef deposits, nice blue water, and life is just thriving. This is probably what the east coast of the United States looked like back around 560 million years ago. Or not 560, we'll say about 540. Well, 560, 540. But minus the trees. The trees did not exist. It would have just been sands and blue water, and maybe some very low-lying mountains. And we are going to end that here because at about 560 we go into life begins to really start leapfrogging. And one of the most fascinating pieces of evolution of life is the Ediacarian biota. And this isn't really, we're not 100% sure how this relates to the evolution of life, especially with us. What we do know is that for the most part up until this time, everything was, basically the most advanced things we had were eukaryotic cells, which, prokaryotic cells didn't have real nucleuses in a sense, but eukaryotes did. They have, they're a much more complex cell. But it seems like life's first event, life's really first push into evolving was to take these cells and start stacking them. So as opposed to specialized areas, like we have cells that produce skin and bone, eyeballs and whatever, that took a lot of time. Life's first attempt seems to have taken cells that were very similar and just started stacking them or grouping them. And that is represented in the Ediacarian biota. And for the most part, these are all made up of the same cells. They just seem to be clumped together, and they can actually form macroscopic. This is the first time that we really see macroscopic organisms come together. And I really don't sure if I call it an organism, but I guess you would. But these are the first time when you just have cells, similar cells stacking on each other to create things that that become visible to the eye. And these are the first real fossils that we start to see. And most of these are pretty much related to, more or less, you would phylum them with plants. However, Dickinsonia, which is, I think this is right here, this actually produced, we found evidence of cholesterol, and cholesterol is only formed by something that is carnivorous or animal. So this might have been one of the first something of an animal found that exists. And this is a fascinating topic. A lot of research is going into it. We don't find them many places on the planet. However, we do find them in Newfoundland, in Canada, and of course in Europe. Scotland, I believe, somewhere kind of in that area. And those two areas were very much connected at one time, and they were very, very warm, shallow seas. And again, that's what I was saying, that life really got its first kick. And it isn't long after this that we actually start to get the life's first explosion, where life starts to do specialized cells. You're able to excrete calcium carbonate from seawater. Things are actually starting to, consume oxygen, and you're really having a whole bunch of different. You're actually seeing almost every single ancestor of the animal and plant kingdom that we see today represented by about 540 million years ago. This particular species, the Ediacarian biota, we do think it plays a role. We do think that there may be descendants of it. Very hard to tell, but evidence is kind of going in the form that, yeah, maybe they might have evolved into arthropods or what have you, or maybe these evolved into sponges. But it's still in the works of, can we absolutely confirm that? We're not really sure yet, but we're getting closer. And these all of a sudden just disappeared. And I might also add that about 600 million years ago, a little later, we had a series of massive glaciations, and we have, obviously, I don't know if you've heard of this, but we have a term we call snowball Earth, and may have been around 700 million years ago. There is a large lip called the Franklin Lip that represents the rifting of North America from Siberia, we think, during the breakup of Rodinia, and it was gigantic, and it may have produced enough material and dust and stuff in the air that it put the world into a worldwide glaciation. And we even think that glaciers and snow extended all the way down to the poles, which means Earth almost got snuffed. I mean, life almost got snuffed out. And yet, it was that just brutal manhandling of life at that time that literally brought us almost to the brink of extinction. Life forms that still, life has a way of just coming back with a vengeance. And sure enough, this is something that came out of that. These, the cells are like, all right, we're going to just try to find a way to survive. So maybe if we group up, it will work. I don't know. But anyways, the Ediacarian biota is going to be in the next lecture, and I'm going to go over it in some detail because I myself find it very fascinating. And I hope you all have a good day. Aloha.